Okay, so I'm going to try to find out the electric field intensity due to a uniformly charged sphere. Okay, uniformly charged hollow sphere. And so, without wasting too much time, let's just I'll just draw the sphere. This is going to be a long derivation because I'm trying to do it in terms of integration. Now, pay attention. This hollow sphere, okay, it's a uniformly charged hollow sphere or a shell, a hollow spherical shell. So many terms can be used. And so let's consider this spherical shell to have a radius of r, which I will write over here. It has a radius of r. Now I want to find out the electric field intensity at this point P. I want to find out the electric field intensity at this point P, and let's consider some basic factors. Okay, the basic factors are going to be, let's say that the distance between this point P and the center of the hollow sphere is going to be smaller. Okay, that's going to be smaller. And let's consider what else can we do? What else can we? Let's consider a small element. Okay, see, in order to find out the electric field intensity at this point P due to this entire hollow sphere, it's not going to be a direct process. It's not going to be a two-step process. Okay, what you have to consider first is an element within that sphere, and so let's say that there is, let's say that there is a small element which I have taken at an angle of d theta from x-axis, which is at theta. Okay, the small angle is going to be d theta. I cannot write it because there's no space. I'll just write it over here. Maybe d theta. Okay, and I hope this. Wait, is this clear? Is this not clear? Okay, so now if you see, the basic element which you're going to take in a hollow sphere is going to be a ring. And so I have taken the small element which basically then gives me or fetches me the result as this. I'll just mark it so that you can see it clearly that this is going to be a ring. What matters is the concept. You have to understand the concept here. And so if this is going to be r, if this is going to be r, then what is going to be the what's going to be the horizontal component of that? It's going to be r cos theta. So I will write it. This is going to be r cos theta. Okay, and this is going to be the vertical component will be what? R sin theta. Okay, it's going to be, I'll just remove this, r sin theta. Okay, so you have a horizontal component of the radius of the sphere that is going to be capital R cos theta, and you're going to have a vertical component that's going to be a capital R sin theta. Now, if I have to find out the distance between this ring and this point P, okay, it will be small r, that is the distance from the center to this point P, subtracted by a small amount of radius of the sphere at the horizontal component, which is the horizontal component. So it's going to be, okay, it's going to be r minus r cos theta. I hope this is clear. I hope this is clear. See, what I've done is basically I've taken a sphere. It has a radius of capital R. I've written it here. Okay, just because this is going to be a long derivation, so I have to make it small. So this element which I have taken on the hollow sphere is basically a ring. Okay, the ring is at an angle of theta, and the thickness is around a thickness of the angle which is being subtended by this ring is going to be d theta. Okay, so now if I have to find out the electric field intensity at this point P, I can start with dE is going to be equal to k dq upon r square. dE is going to be equal to k dq upon r square. And now if you see this r square, the small r square, it is basically the distance between this point P and the element which we have taken. So that will give us the distance in this way. Okay. And this distance is equal to, you can find out by Pythagoras theorem. Okay. That distance is going to be what? Okay. It's going to be the horizontal component, the horizontal, that is the adjacent, r minus r cos theta, Pythagoras theorem, r minus r cos theta, and the vertical component, that is r sin theta, r minus r cos theta, r sin theta. Okay, so I will write that dE is going to be equal to k dq upon r minus r cos theta whole square plus r sin theta whole square. Small r, okay, so the small r square is basically the distance between this point P and the ring, and that I can write it as this. Okay, now what else can we do? Look at this dq. Okay, it's a small charge based on the element which we have taken, that is a ring. I can write it in terms of surface charge density. Surface charge density can be written as sigma is equal to charge per unit what area, charge per unit area. Okay, so I can say that dq is going to be equal to what? Sigma times dA, sigma times dA. And so I can say sigma into the area of the ring, which is basically what? Area of the ring can be found out by multiplying the circumference of that ring, which is going to be the exactly equal to the circumference of a circle, and I can multiply that with the thickness of the ring, and that will give me that should fetch me the results, that is the area of the ring. It should fetch me the results. And so I can say that looking at this ring, I can say that the circumference is going to be 2 pi capital R sin theta. Okay, why R sin theta? See, look here, the sphere has a radius of R. It has a sphere of R, and let's say that radius is around here, this red line which I have made. Okay, that's the radius. So if I have to find out the radius of this ring, okay, considering that this is a three-dimensional thing, the radius of the ring is not going to be same as the radius of the sphere. Okay, it will start at a different point, maybe at the center of this ring. Okay, maybe at the center, and so that will be the horizontal component of R. That has to be the horizontal component of the radius of the sphere. So that is why I am taking r sin theta. Okay, if there is any doubt in this, please let me know later on. You can send me messages, or you can email me. I'll forward it to you if you require. And so dA is going to be what? 2 pi r sin theta into thickness. Thickness is going to be what? As I explained earlier, the thickness is going to be r into d theta. Let me give you a small example. Okay, if this is the radius, okay, if this is the radius, and if I expand this, it's going to be basically what? The length is going to be still the same. That's the radius itself. The length has to be the same, r. But the angle, if I multiply the radius with the angle, it's going to give me the thickness of it. It's going to be it's going to give me the thickness of, okay. So I can write the thickness of the ring in terms of theta and r, and what I will get is r d theta, r into d theta, because d theta is the angle which is being subtended by the ring at the center of the sphere. Okay, so now what I will do is basically substitute what we have just found out is small amount of charge, which can be written in this form. Okay, that's not small. So we'll write that in that format. And so I'll just rub this due to lack of space. And what we will get is dE is equal to k into dq, which is sigma times, okay, circumference of the ring, that is 2 pi r sin theta, okay, into thickness of the ring, r d theta, upon, it's going to be r minus, this is the distance between the point P and the ring. Okay, this is the distance between the point P and the ring, this small. And of course, the root, square root gets cancelled. because it's squared, because the small r is basically squared. Okay, so now this is going to be the electric field intensity at this point P, but in what direction? It's going to be in this direction, and that's what we don't want. We want it in terms of x-axis. We want it in this direction, and so I will take the component of this radial direction on x-axis, and that is to give me cos theta. That will be in terms of cos theta. So I'll write here dE cos theta is equal to, okay, instead of writing here, I'll just write the, I'll just do it over here only, because okay, it's going to give me the same thing. Okay, I just multiplied cos theta on both sides, and so d cos theta now gives me the component of electric field intensity at this point P on the x-axis direction. Okay, now it's going to get more complicated, and let's see how. Okay, look at the diagram. If you look at this diagram, cos theta can be represented as what? Cos theta can be represented as what? Isn't cos theta basically r minus r cos theta upon, okay, I have not written that over here, but I'll just write that. It'll take a lot of space. Square root of small r minus r cos theta square plus r sin theta. Okay, so it's going to be this. It's going to be the addition of r minus r cos theta. Okay, and the hypotenuse, that is root of small r minus capital R cos theta plus capital R sin theta whole square. So I will substitute that accordingly in the place of cos theta. I'll do that. I'll substitute that. What I'm going to get is basically k sigma 2 pi r sin theta into r d theta upon small r minus r cos theta whole square plus r sin theta whole square, okay, into cos theta, which I said is adjacent, that is I'll get r minus r cos theta upon square root of this hypotenuse, that is going to be, okay, is this r minus r cos theta whole square plus r sin theta whole square. R sin theta whole square, and this is going to this is a very big equation. This is a very big equation, and so let's simplify this. Okay, let's simplify this, because integrating this will take us a long time. The way to you see make it easier is to reduce the terms, and so let's simplify this. Okay, I will write this down again so that it is easier to understand. So if we simplify this equation, we are going to get, I'll just even rearrange the terms. So you can see k sigma 2 pi r, and there's another r, so I can write 2 pi r square, and then I can write sin theta d theta, and then I also can write r minus r cos theta upon okay, this entire thing, if I simplify it, it's going to be r minus r cos theta whole square plus r sin theta whole square whole raised to 3 by 2. Sorry, this whole yeah, so the entire thing, that is r minus r cos theta Yeah, should be equal to the same thing. Should be equal to the same thing. And so if we go to simplify this equation, you can see that r minus r cos theta whole square plus r sin theta whole square can be simplified using a minus b whole square, and you can simply simplify it. And so what you'll get is k is this visible, k sigma 2 pi r square sin theta d theta r minus r cos theta whole upon. Now let's simplify the equation, and this is what we'll get. Okay, you get r square, okay, plus r square cos square theta minus 2r cos theta plus r square sin square theta whole raised to 3 by 2. Whole raised to 3 by 2. And so now what we can see over here is that r square cos square theta and r square sin square theta will help us to give us sin square theta plus cos square theta will give us 1. And so I can write, and what else can we do? Yeah, that's what we can do. And so I will write that. I'll just do that. I'll just write the changes down. So what we'll basically end up getting is r square plus capital R square, okay, minus 2r cos theta whole raised to 3 by 2. Whole raised to 3 by 2. This is what we are going to get. So ultimately we have simplified the denominator. We have simplified the denominator. Now if you see, I have written this sigma over here, and sigma means charge per unit area. Of course, we already had substituted charge per unit area. You will say that that I've already, that is let's say sigma is equal to q by a, and I have written it as what I've written it as dq is equal to sigma times dA, and I have substituted. Now remember this, that I have substituted the area, which is basically the element, that is dA. dA is basically this ring element, okay, but I can also mention that dA is a ring element in the entire sphere, and so I can write sigma separately as q, capital Q, upon, considering the fact that the entire charge on the hollow sphere is basically a capital Q, and so I will write sigma as capital Q upon the area of the entire sphere 4 pi capital R square. So sigma can be written as Q upon 4 pi R square, and you can see sigma right over here, and that is what I will do. So when I do that, it will help me to reduce the equation in a much better way. So I will write that down, that K Q upon 4 pi capital R square into 2 pi R square sin theta d theta r minus r cos theta upon this entire term, that is r square plus capital R square minus 2r cos theta whole raised to 3 by 2. Just a minute. Yeah. Is that visible? No. Just a second. Yeah. Just write that down. And now you can see this capital R over here gets cancelled with this R, and this pi gets cancelled. This 2 gets cancelled. What remains is 2. What else gets cancelled? That's about what gets cancelled. And so if I write these terms again, what I will get is after cancelling with the charge density, I'm going to get this, that is k cube, okay, sine theta d theta, okay, r minus r cos theta upon, we got 2, okay, we have got the term 2, and we're going to get square plus capital R square minus 2r cos theta raised to 3 by 2. Finally, we get something like this, and now I can tell you that we are ready to integrate. Yes, of course, it's still looking a lot more complicated, and that complication can be removed with the help of substitution, and so we'll look over that. So now I have found out dE cos theta. Okay, that is the electric field at the point P in the direction in the x-axis direction. And so now I want to find out what E is, and basically E is going to be an integration of dE, which will be equal to what? Now, what are the constants in this? Is K a constant? Yes. Is Q a constant? Yes. 2 a constant? Yes. Okay. These are constants. Any other constants? Sin theta, d theta, and this R is associated with this theta. Even this is associated with an angle theta, and so none of them are constant. So I can directly write integration of sin theta d theta r minus r cos theta whole upon r square plus capital R square minus 2r cos theta whole raised to 3 by 2. Whole raised to 3 by 2. And so now let's start to integrate it. The best way to integrate this is to take this entire denominator as t. If we take this entire denominator as t, what we can probably do is solve the equation in a much better way. I will write it down over here, and I hope you all can see. Okay, this turn the angle, and this is going to be equal to, okay, r square plus capital R square. This is the denominator which I'm writing, minus 2r cos theta. Okay, 2r cos theta. Let's consider that to be equal to t. If that is equal to t, then what is the difference? Okay, if you differentiate it, this is what you'll get. This is 0, this is 0, because these are constants. Theta is a variable, and t which I'm taking is also a variable. So I will get minus 2r cos theta's differentiation will be what? Cos theta's differentiation will be minus sine theta. So I will write minus sine theta equal to dt equal to d. And so ultimately what I'll get is 2r. I will get is, this is, yeah, 2r sine theta equal to d theta equal to dt. 2r sine theta d theta equal to dt. Now if you see sine theta d theta, sine theta d theta here can be substituted as dt upon 2r. So I can write this sine theta in terms of that, and I can substitute this entire denominator as t. That makes it much easier for me to integrate. Okay. Okay, so I've just rewritten these terms again, and you can see that I've written the denominator over here above. I've written it as equal to t. When I differentiate it, what I will get is 2r sine theta d theta equal to dt, and sine theta can then be written as dt upon 2r. One more thing, if you see in this equation, is that the small r minus r cos theta can also be, it also can be, it can also be what you say, simplified. And so I will write that the r minus capital R cos theta, okay, will be equal to what? What can it be equal to? I can write cos theta as what? I can write cos theta as what? Think about it. Think about it. I can write it in this form, isn't it? I have cos theta over here, so I can convert it in terms of t, isn't it? There's a cos. I've just written here cos theta here. I can convert it in terms of t. So let's do that. What will be cos theta then over there? I'll just write it here. Looking at that expression, can you tell me what this cos theta can be? I'll just remove this cos theta. What is it going to be? It is going to be, okay, let's do it. T minus, okay, it's going to be say, or let's yeah, it will be r square plus capital R square, okay, minus t upon 2rr. R square plus R square minus t upon 2rr. Yes. So that is what you will get. And now what else can we do? We can simply cancel this capital R over here. Once we have cancelled that capital R, we can write it as, we can take, I'll just erase this capital R over here. So ultimately what we can write is, if you take the LCM, you'll get 2r square, okay, minus r square, okay, minus r square minus capital R square plus t whole upon 2r. And then you'll get 2r square minus r square, that will give you r square minus capital R square plus t upon 2r. Oh, wait, 1 minute, it cannot be seen. So this is what you will get. 2r square minus r square will give you r square minus capital R square plus t upon 2r. Okay, this is what you will get. So this can be substituted in terms of small r minus r cos theta. Okay, so I'll write this equation once again. Yeah, so ultimately what I've done is basically with the substitutions that I had done previously, which I had showed you previously. The only thing is this sine theta d theta, I've written it as dt upon 2rr. This r minus r cos theta, I have written it as this term. And this denominator is entirely taken as 1 upon t raised to 3 by 2. 1 upon t raised to 3 by 2. So now let's remove all the constants. So if you see here, you'll get kq upon, let's remove all the constants. That is 2, 2r, 2r. So what you get? 2, 2, 4, 4 to the 8 r square r whole upon, okay. There's some audio problem. dt upon t raised to 3 by 2, and you get r square minus capital R square plus t. Okay, this is what you'll be getting. Apart now, how can we solve this? How can we solve this integration? Let me rearrange the term. I can take dt over. Okay, so right now I can say that I can group r square minus r square like this. Okay, I can just group it, no problem in grouping it. And I can take t raised to 3 by 2 on the top. So what I can get is basically kq upon 8 r square capital R whole of integration r square minus r square t raised to minus 3 by 2 plus t into t raised to minus 3 by 2 dt. This is what I will get. And now what can we do after this is basically just simply start what can we do is basically simply we know that this small r and this capital R is again a constant. We can take the integration in that way. Let me put a bracket over. So what we will get is basically equal to kq upon 8r square capital R. Okay, and instead of this integration over here, I'm going to take it right over here. So I will write this bracket again, r square minus capital R square. Okay, integration of t raised to minus 3 by 2 will be t raised to minus 3 by 2 plus 1 upon minus 3 by 2 plus 1. That will give me t raised to minus 1 by 2 upon minus 1 by 2 upon minus 1 by 2. Okay, is that visible? That's visible. Okay, plus t. Okay, integration of this entire thing, that is going to be integration of that entire thing. So that will be equal to what? First of all, we have to add this t raised to minus 3 by 2 plus 1. That will be minus 1 by 2. So I can write it as t raised to minus 1 by 2, and integration of t raised to minus 1 by 2 will be t raised to half upon half. This is what we will get right now. Okay, this is the most simplified version of it. I'm going to write this all over, write the last equation on the top, and so we can continue. So ultimately, this is what we get, and then we can take minus 2 on top. So I'll write that again. Aq upon 8 r square r. Okay, minus 2 r square minus capital R square t raised to minus 1 by 2 plus 2 t raised to 1 by 2 dt. And now I can remove 2 out. If I remove 2 out, what I will get is basically, I'll just remove 2 over here. Remove 2. Okay, so I got 2, and then 2 ones, and then I can write 2. Okay, so this is what we ultimately get. I'll just reverse the terms for simplicity. So I will get kq upon 4 r square r. Okay, I can get t raised to 1 by 2 minus r square minus r square raised to minus 1 by 2 dt. Sorry, I'm sorry, dt won't be there because after integration dt is gone. Okay, t raised to minus 1. So looking at this equation, which is finally simplified, of course, this t raised to minus 1 by 2 can be written as t raised to 1 by 2. And now we know what t was, that entire denominator. Okay, so if you've written in your notebooks, you can resubstitute it. And what we'll get is kq upon 4 small r square capital R. Okay, we will substitute that entire equation in terms of t, and that is what this is, t raised to half. So that means it's square, there's a root of it, and we're going to get r square plus capital R square minus 2r r cos theta. Okay, minus this r square minus capital R square upon the same denominator. There's no space for a right. It will be r square plus r square minus 2r cos theta. I think that is not visible.